I think we're all good now. Welcome, everybody. This evening, I'd like to talk about what I'm calling Newbots. And to me, that's really just an attempt to apply some labels to what I view as inflection points in the progression of robotics in the past about 20-year time scale. This is kind of a rough, so I would like this to be an interactive session. Please interrupt me if you have any questions or comments. I actually really enjoyed preparing this because I got to dig into some history and clarify a few things, but let's go ahead. So I think the fundamental challenge is identifying what's actually an inflection point or what we would call a label. And when it comes to robotics, the reason why, okay, so I'll talk about some other places where we have version numbers or like attempts to create version numbers. So at the top, we have the wireless telecommunication versions throughout the years. Those are pretty straightforward and easy to understand. That naming scheme has also been used since the beginning. They were always marketed that way and discussed that way, and that's a very straightforward one. That's also only in about the past 10 years. Wi-Fi is a little bit more interesting. Initially, it was just discussed as being, the 2.4 band, 5 band, and now that there's Wi-Fi 6, which isn't actually on 6 gigahertz band, it sounds like it was actually there was an attempt to back version control Wi-Fi since the BGA, AC, etc. got too confusing and hard to market. So the Wi-Fi Alliance just said, we need to give version numbers to this thing. So I guess Wi-Fi 4 and 5 are actually industry names now after it just got too confusing for everybody to talk about A and N and G and B and these sorts of things. The one that gets to be a little bit more interesting is the evolution of the web. So, there was the web 1 and 2, and now we're, I think, arguably right in the transition of web 3, depending on who you talk to. And that one is a bit older and much more interesting. The thing about the web, though, is I would say that the tools powering the web are actually, there really aren't that many. It's pretty high scale. It's low mix, high volume. So like the internet is largely served by Nginx and Apache. And those are kind of the main two technologies. There's a handful of other things that come up and frameworks that come and go and these sorts of things. But in large part, it's really, I don't think that many things compared to robotics. And then the really heavyweight one at the bottom I've listed is the Industry 4.0 label. Industry 4.0 was coined, I think, maybe 10 years ago and is referred to as the fourth industrial revolution. So this is referring to the evolution of an entire industry over hundreds of years. For the purposes of our discussion, robotics, I think, is going to be right in the middle between some of this web technology numbering and putting a number on the the entire industrial production. Okay. So the main issue with trying to figure out how to do this with robotics is just the incredible scope of any robotic system. It encompasses many different disciplines and vendors and technologies. And I think the central limit theorem applies there, where if you think you have an inflection point or a big change in one, that just kind of gets evened out by the waves in the other, and it becomes a bit of a head scratcher to see if there's actually a distinct point that's formed. So there's that. The other one is that robotics is really not standardized. There's many different vendors and applications, and many of them are kind of really long tail, low volume things. And so unlike something like the web, where you have a short list of web servers, or the industry, where you have a short list of processes, robotics is just this really long tail in a lot of different ways. Okay, so this is my first stab at like the core features that we might look at if we're trying to figure out if we're in a new era here. So I've grouped them into three main considerations. The first would just be the approach in the system that's being built. And there's four main things to look at here. And this is all like a compare and contrast. So in the approach, there's like the repetitive versus adaptive. There's, just a few robots that are really quick and speedy versus many robots that are cheaper and slow. Then there's defining behavior in hardware versus software, and evaluating and designing system at a kind of a cell or individual process step level versus a overall system that's working at the same time in a fully connected manner level. And then I think there's a couple key technologies that have emerged that you can look at and see what people are using. So the big one is you'll see a fixed robot versus a mobile robot. I think that's a big telltale sign. And then the second one that I've tried to put my thumb on it, but I think it's something like a sensor limited versus a compute limited implementation. That's the second one. And then the last thing that I think really what it comes down to is like Newbots today, like a robot company today is something that can be prototyped in a garage. Like literally, you can just have a few people build a minimum viable system in a kind of prosumer environment, versus a traditional robotic system is usually going to be found in a warehouse, and it's very capital intensive to even build one or two. So the barrier to entry just in resources and space is much lower today. To give a little, yeah.
Sorry. By the move from fixed to mobile, is it in the robotic industry, do we think a typical arm robot as mobile or not mobile?
An arm robot
I'm asking because traditionally robots, when I was a child, so a long time ago, a lot of the robots were the big robot arms for making cars, okay, on manufacturing in factories, basically, okay? But
yes,
for me, it's a robot arm, so it's mobile in the sense that it moves. But here, maybe you're talking more about mobility in terms of it's moving around, basically, right?
Yes, I mean that it contains its own power system and is capable of locomoting beyond its reach. If maybe that's a good definition. So it can actually move beyond its reach in the strictest sense of, like, let's say it has some actuator or a linear slide or guide or something. It's not just like a one travel. It can actually move throughout the environment that it's designed to exist in.
Okay. Thank you.
But I'll talk a little bit more detail. I didn't really get to flesh these out more, but we'll get there. Any other questions?
Yes, another question is on the fast, expensive, and slow, cheap. Would you have some concrete example? I wasn't totally clear about
I have many examples. Yes.
Oh, wow. Okay.
I have, at the end, I have many examples. Those will be fun.
Okay, so let's wait then. Thank you.
Okay. Any other questions?
So there is a move basically from the last line, so warehouse to garage. So there is a move from the industry to the home or to the service. How to put it? That now we
that
can have robots at home. Basically, we have the Roomba, right? 20 years ago, it
I
was
don't.
not.
Yeah, so I don't mean that in the literal sense of like it being a robot applicable to the home versus an industrial use case. I mean the literal capital intensity to build a single robot that provides a minimum functionality. The Roomba is an example of a robot that, let's say the Roomba didn't exist at all today, and somebody wanted to create a robotic vacuum cleaner. The Roomba could be prototyped in somebody's, spare bedroom with a 3D printer and some off-the-shelf parts. That's something that really wasn't the case, maybe 10 years ago, maybe, but yeah, 20 years ago, it would require, actual some capital and maybe a couple people to design it, and just the tools weren't there. Like the infrastructure wasn't there, the rapid prototyping wasn't there yet. And so the capital intensity to create a Roomba today is that which, somebody in their own household could do solo in a small room versus an actual corporation with a team and all of that. So that doesn't mean a literal, like a robot that's applicable to one space or another. I just mean that in kind of an easy to remember capital intensity way.
Yes.
Does that make sense?
Yes.
Okay. Okay, so this is my attempt at a timeline and some key goalposts or bookends that mark those timelines. So I would consider the beginning of robotics to be the first Unimate that went into GM in 1959. That's the first robot that was doing serious things, and then they made many more, and it had a meaningful impact on kind of an economic function. So that was, the beginning of the 60s. The next bookend, I would consider this to be, and this is arguable, but I would consider that bookend to be Kiva Systems and the Roomba. The Roomba 1.0 was launched commercially in 2002. Kiva Systems was founded in 2003. I think those are two kind of canonical examples that I'll talk about why that is later. But those are two really important robots that came into existence. And then the other one is Willow Garage, was founded in 2006. And the output of Willow Garage is extremely significant today, and I think will always be. So that's why I consider Willow to also be in this kind of 2002 to 2006 bookend. So I would call that Robotics 1.0, or like the first version of robotics or traditional robotics is that time span. The thing that I think is much more up for debate is whether there is an intermediary era that's between then and now. One could argue that we're still in the same era, but I do think there are some other arguments that there may be a 2.0 that kind of showed up between then and even about 3 to 5 years ago. I actually think there's a very strong argument that the Jetson, the NVIDIA Jetson, is in its own right the beginning of an era of robotics. I think that's still yet to be seen, especially with the competition from architectures like RISC-V. But if you don't count that as being a bookend in its own right, then we're still in the era since 2006. About the past 15 years is this new era of robotics. So that's my stab at the timeline.
I don't feel like we're in 2006. I mean, I can't put it in words, but I definitely feel that a few years ago, something changed. I don't know what to call it. But when you talked about the garage, so yeah, that changed. There's parts, there's easy to do integration, there's an ecosystem. Like you feel that it's just, continuous slow improvement from 2006?
No. So 2006. Keep in mind that to me that was the inflection point. So,
Can I say something regarding that?
Yeah.
2006 was the year, like the beginnings of ROS. So I would like put a mark there, because like everybody was doing their own middleware before, but that was the time like people started using some sort of common framework and middlewares.
that's why I have Willow Garage
Yeah.
here. So
Yeah.
I initially that Ross is the reason why I list that date. Otherwise, I would just say Kiva Systems was the bookend, but that's why I've listed 2006.
And
But
Arduino also
no-
started in 2006, right? I'm looking at Arduino's Wikipedia page now. That was also started in 2005 and 2006. It started going up. So you can say the maker revolution started around the same time in parallel. So that also lines up.
Yeah,
2006, absolutely. But I'm saying 2016, 17, something changed. You know, maybe all the little pieces came together. Just a feeling that I have.
this is why I've listed the grayed out 2.0, because I think depending, I mean, I preemptively put this here because like I say, I can't distill it, but I also can't think of anything that's as strong as what happened in the 02 to 06 band. So that's why I've listed it as a soft potential intermediary step, but
Maybe also 3D printing became more, let's say, cheaper and more available. So around, I think 6 years ago. So in like all the things needed for making Otto, the robot, could have been done in 2010, 2006. But yeah, you didn't see like robots like that at that time, like so cheap and easily like makeable. But I think 3D printing also comes into the picture.
I would completely agree that the single largest maybe in inflection contributor is additive. Additive has been around for longer than just that time frame though. That's the thing that makes me hesitate. It's not like there was one patent that expired that created the onslaught. I mean, the Stratasys controlled temperature patent allows you to print stuff more accurately and certain materials and these things. But you know, the cupcake CNC, the first replicator, that was somebody want to look that up? I think that was well before 2010. Like the first MakerBot cupcake CNC that was all laser cut plywood. Oh, actually, no, that wasn't the one. The other one was it was all threaded rod and 3D printed components so that it could be fully replicable on itself. And Home Depot.
I think there's two parallel timelines here. One is enabling technologies, and then there's like the kind of social ecosystem boom that tends to happen 4 to 5 years after it. So there's like so if you try to put both events on the same timeline, the story gets a little confusing. And yeah, I think there's some ambiguity in the 2006 to 15 or whatever window. I would also argue that there's probably a point somewhere around 1974, because it shows up in the economic data. There's a famous paper called 1974, which shows that lots of things suddenly went through an inflection. And that was one theory of it was factory automation finally kicking in. So that's another like social versus enabler. I'll try to find the paper and post it. But yeah, I mean, this story looks plausible to me.
Yeah, I will say, Mayor, I'm missing additive. Additive is certainly in its own right. It should be a line item here. So that definitely should be considered part of the critical tooling.
In order to do home, yeah. In other words-
Not just home, not just home anymore. I mean, the number of things that are in production off an additive process are increasing exponentially. So that in robotics as well. So that's a big deal.
No, I understand. I'm just saying that if you have a factory with a machine shop, you can build anything, but at home you can't. But with additive, Venkata showed us what you can build.
Right, but the issue was for a long time, additive was strictly for prototyping and considered part of a rapid prototyping process. The thing that's happening is additive is actually becoming a manufacturing method.
Yeah.
For robots. Robots were usually made out of metal, and then additive metal was not a home thing, and still really isn't. It's getting there, but still really isn't. So additive polymeric, that's why I consider the Roomba to be so critical, because the Roomba is structural polymer. That's what the robot is composed of. It's a plastic robot. It's like the first plastic robot, which is a big deal. Before that, there wasn't any like high volume consumer electronics plastic robot. So you could produce you could 3D scan and print a Roomba at home and actually manufacture a replacement part for your Roomba at home today. That's the thing that I'm saying.
Yeah.
Okay.
I just one last question on this thread. What about the whole issue of drones?
Drones. I think my hot take is drones they had a pretty tall peak of inflated expectations. So drones almost don't count in a lot of ways. I think, the most successful drone would be a DJI product. And in terms of like the actual number shipped, I mean, that's not a negligible number. That's a pretty big number. I actually don't know what DJI's shipment is compared to Roomba. Roomba, I think in total has shipped around 18 million robots. But in terms of like actual useful functionality, I really, at least for consumer drones, it's really not there. It's like GoPro, how's GoPro doing? It's a camera that flies. I don't know. I just don't see drones as being a huge deal yet. I have a few examples of drones doing real things that could actually be super valuable in the long term. So I think drones are finally starting to become a more usable thing. And especially tethered drones are actually very usable in a lot of cases. Like a battery operated drone isn't very useful, but a tethered drone is extremely useful. But in terms of it being like a significant enough thing to have its own inflection point, I don't view it that way. I don't think drones in the 2010 time scale, when a bunch of money went into them, is actually very significant.
Would that be because most of the drones that we can see in the market basically are remote controlled? Okay, so I'm not sure they qualify so much as a robot in a sense. They are doing more and more automated stuff. Not the guide, the stability and stuff like that. But still, basically, they are remote controlled, right?
Yeah, and they also usually aren't doing something that is fundamentally enabling. They're collecting data, but we've flown planes over cornfields for many, many years and get really good data out of that. So like I say, there are some successful drone companies and that are using them as robots, that are using them in an automated fashion that actually run a canned or even adaptive flight path and go inspect things. But it's really, I don't view it as being like this is something you couldn't do at all before.
Mm. Yeah. Thank you.
Like, to me, the Roomba is something that the world never saw at the scale that it was deployed in and the way it was made and the price that it was. There's just a bunch of things all at once that happened. And they're still going strong today. But yeah, early drones were also RC. So yes, that's to your point. Yes. Like the number of drones that are a robot in the adaptive and autonomous sense is actually pretty low compared to the number of drones in existence, versus every Roomba is autonomous. What do you think? What do you think, Mayor?
I think you're right. I'm just thinking from a technological point of view. Again, you know, something happened. Now everybody has a small drone in their pocket. Yeah, it's not a robot, but that's because the software part isn't there yet. And I agree what you say about the use cases. There are a few popping out, but none of them have actually exploded on the market.
Right.
Okay.
Okay.
So, I still haven't been able to make sense of what happened in the last 5 years, but okay. It's fine.
Got you. Yeah. What's yeah, maybe some of the examples will shed some light on that.
Yeah.
Okay. Yeah, so to dig into, I think we've already kind of dug into this a bit, but to dig into the defining factors. So the repetitive versus adaptive functionality, I think, is actually one of the largest things. So using the Kiva systems as an example, those robots went from being a single track guided system to an adaptive system which changes to conditions and also allows changing conditions, changing. It's also a fleet, right? So they interact with each other, and just like as an approach, not needing to only focus on repetitive tasks opens up a whole new spectrum of functionality. The few to many distinction, this one is harder to characterize, but it's a defining feature for sure. So Kiva Systems is the best example of that thus far. The throughput of that system compared to a conveyor belt was way better, and a lot of that had to do with the fact that a goods to person system, which is what it was used for, is high mix. So the conveyor belt's very good at one line of things, high throughput, but when you start mixing stuff up, it doesn't work, right? Because you need to route things from different distances and lengths. So actually having an adaptive system that is many more slowly moving robots, it ends up being disproportionately better to just have a bunch of slow things instead of one really fast thing. The other thing is, this comes back to the capital required to build a robot. You can build a robot that does a lot with a very small number of tools and money. So a thing that actually moves around and does the thing has gotten very small. So that allows you to just build as many as you need to achieve a system throughput. Building one giant thing that's really fast works in some situations, but it actually turns out especially if it's a higher mix or not just the same thing. Like a potato chip slicer is a great machine to build one of, because It's very consistent. It has the same input product, but it's not adaptive. A potato sorter, on the other hand, that actually needs to look and adapt and reject things, that ends up being, if you look at those machines, they're actually a collection of little paddles. So it's usually, I don't know if you guys have seen like an optical sorter, but you'll have a row of like 10 or 100 little paddles, and the tomatoes or potatoes or whatever agricultural product will roll by them on a conveyor, and then it'll scan each one and hit it with its little paddle. And so that requires a large number of structures that are actually doing their own thing. But I wouldn't really consider an optical sorter to be a robot. That's an example of a piece of traditional automation. But as an approach, that's something that allows you to use adaptivity to achieve very high throughput with many copies of something. Okay, so the hardware versus software thing. So I want to use I don't know why this comes to mind right now, but how many of you have ever tapped a hole in a piece of metal? Everybody tapped a hole? Okay,
What
so
do
some
you mean,
people have,
tap the hole?
like, to actually create threads in a piece of metal, you need to first drill a hole, but then you have to cut the threads or form the threads. So
Okay.
you like drill the hole and you remove the material, but then you need to make the threads. So usually when you do that, you actually need to like move the tap in sync. So you need to spin the tap that makes the threads, and you need to move the tap down at a rate of speed that matches the rate that you're pushing it in. Otherwise, you can damage things, right? So it's like trying to insert a screw at the same rate that you're spinning it. The old school way of doing that is you just create a mechanical system that has springs and it allows some swap or misalignment. But today, the way you do that is you just have a number of sensors and software that synchronizes everything. So I'm just trying to say there are many mechanical systems and mechanisms today that instead of building a dedicated mechanism to serve some function, you would actually just use a software component to synchronize things and close the loop. I don't know, I should think of a better example, but it's just componentizing software versus hardware is the thing that you'll see. And then I think at the actual planning stage, part of this is the tooling available, but designing the system based off of a system of robots or many robots or many elements in the system is usually the approach you're going to see, instead of just like a car production line where you have individual cells that all run at a specific frequency. That's really easy. It's like you have however many seconds per cycle, and then every single system has to conform to that. But it isn't actually, there isn't crosstalk between systems. And when you start having adaptivity, you need to have the system performance and modeling up front. Like there's no way to really figure out how fast a fulfillment center is going to spit out products unless you model the system. There's no like back of the envelope, mean path, and it really is, it's sufficiently complex that you need to holistically model it. And I'd say that's becoming the standard practice, is you actually simulate the system up front as a design element. Okay. The enabling technologies. So the question about, is it a fixed or a mobile robot? Yeah, so getting the thing to either literally, grow legs and walk away or roll away. We have batteries that can support that now and motors that can support that now. This is something that we just didn't have in 2000. Lead acid batteries only went so far. So we definitely couldn't do drones with lead acid batteries. Meyer, I think that's a good example of something that flying things, especially, small flying things have been changed by batteries in ways that are profound. The rare earth magnets allow us to have legs. We couldn't have robot legs before rare earth magnets. So that's a pretty big one that allows us to go mobile. The second thing, compute versus sensor limitation. So I think cameras and LiDAR generate so much data that the compute is still long behind what you need to have kind of like a level of functionality. Like before cameras are really cheap, like in what would the example be? I could talk about the Roomba, I suppose. The Roomba is kind of an odd one, because the first Roomba actually had a very at the time it was a lot of sensors, but they were all individual single points of data. So there's like some proximity sensors and a bump sensor, and it had maybe a dozen or so sensors on the robot. And that's a very sparse amount of data. Like the compute required to do anything to like consider that data in a fully meaningful way is very low compared to more recent generations of vacuum cleaning robots, including the Roomba, which now have a camera. So the ambiguity involved with computing the meaning of sensor data is now very high compared to when you just had a few bump sensors and things. And I think this is the status quo. Every robot today has cameras and or LiDAR or some other 2D or 3D sensing element, which creates a very large volume of data. And this data is just, it still is overwhelming even the cutting edge of, TPUs and NVIDIA products, all these things. So if the robot doesn't have enough sensor data to kind of like scratch its head, I think that's a sign that it's not really using a modern approach. And this is what you'll usually see in kind of traditional automation, industrial automation, is you'll see very sparse sensor data versus the modern Newbot approach would actually to have a camera.
And have a Jetson Nano to process the image on board. Yeah.
Yes, but even the Jetson Nano is often still not enough to keep up, or even a full-size Jetson for that matter.
I've already seen clients that are using a Jetson Nano in order to do on-robot image processing, which enables whatever it is they're doing.
Of course. My point is just that whatever they're doing with the data is just the minimum required to get what they need to get done. There is so much more that you could get out of that data if you wanted to. And it would require more compute than you have. So the compute is the scarcity now.
Okay.
I don't think I'm characterizing this very well. So
I think you did. I think what you just said was that these robots don't have a surplus of processing, and therefore, even though they're out there and collecting a lot of information, we're actually not getting all the benefit we could out of it because they don't have a surplus to process it. That's a very interesting, what the next step could be.
Yes, precisely. The sensing and the perception is very much creating a surplus. It's
computing.
inference that's, yeah.
I can just say that when we're talking, Eric and I, about what we're doing on our platform, we talk about the robot learning, but we're not talking about doing something else with that data. You know, something extravagant. So that's an interesting growth direction.
Right. And so the whole premise of that discussion that you could do something extravagant with the data is new, compared to only having, you know, maybe some touch sensors or force sensors or whatever. There really isn't anything luxurious or extravagant that can be done with such sparse data, which is what you usually had before. So cameras especially were game changers.
Are you including storage and compute? Because many of the smaller robots, what I hear is even just storing the video footage for later processing is the bottleneck. Like, forget getting to processing or throwing machine learning at it. You don't even have enough like onboard storage to save all the imagery. And you don't have like reliable enough network connectivity to like, you know, send it to the cloud. So even that's not resolved, I think, because storage is pretty expensive. If it's like, you know, if you have like 6 color cameras pointing in various directions running at like 30 FPS or something, and you actually wanted to log all that, it would be, I don't think you could do that. Like, you couldn't carry enough SSGs to do that in small robots.
Yeah, precisely. Yeah, that's exactly what I mean. And I do mean compute to just be like an overarching,
Okay.
everything that is on the other end of that camera. And today now, many cameras. So yeah, if you have a dozen cameras that are a very small fraction of the total BOM cost today compared to what you might be 5-10 years ago, the whatever hardware you have that you're spending money on or power on is not going to be able to keep up with even modest amount of processing, storage, transmit, receive, etc. So that's, yeah, that's all I mean to say with that. Okay. Yeah, the tool availability, I think I can clean up this slide, but yeah, so Mayor, that's what I mean is the capital, the upfront capital to build a robot that does the thing is extremely low. I really think it's like 10x in the past 10 years or so. And that's a big deal, especially when it comes to the new introduction of robot approaches and the really, really long tail. So I'm very familiar with agriculture. Agriculture has this problem where the individual products have different needs and sizes and machines and things. And so there isn't really like one upfront investment that catches them all. Unlike you might have with fulfillment. Like fulfillment has this nice property where if you just invest a bunch of capital into a couple companies that produce a solution for that space, almost everybody can use it. So especially the CFCs that you have today, they're usually serving many customers. It's not just one customer, it's a mixture of brands. And that's all, that capital investment is, the yield from that is seen by everyone. In agriculture, you don't have that. So it's actually a big deal for the upfront capital to be low to build a minimum viable thing, because the total net return on that is going to be pretty low compared. So this means that a lot of robots are coming into existence that nobody was motivated to before, and therefore it's a really big deal. So the robot in a garage versus a robot in a warehouse is a big deal to robotics, because a robot in a garage is often all you really need.
Can you say that again?
Let me
A
say that
robot
again.
in a garage is all you really need. Can you explain?
Yeah, I just mean I could give you an example. Like all of the lettuce in the United States is grown near me in the Central Valley, and then in the winter months, it's grown in Yuma, Arizona. It's like almost all of it is grown in those two locales, depending on the season. So it's like if you want to build a robot to harvest lettuce, it's very easy to talk to all of the people that would ever want anything to do with that robot, and just a few people building that robot in the garage is really all you need to complete that product or that solution. And it's all you should need, because if you needed more than that, it just wouldn't make sense. It would require too many resources to do a small task. So I'm just saying, like, in terms of in the business sense, in a capitalist system, like, you have to have motivation to justify the investment. So if a few people can get it done in a garage, that's great, and that's all it should be. It should be no more, because if it was more, nobody would be incentivized to actually go through with that and automate the task.
So to put it like this, developing a robot is not something you need a big company to do, but it's something that an engineering corporation can do as a one and done project. It's like the equivalent of a garage.
Yeah, it's almost like system integrators that are you familiar with a system integrator? That's like an industrial automation. There are these middle people that do all these weird small bespoke projects.
Yeah.
Most system integrators don't build robots, though. It's outside of nobody, they don't really do Newbots or mobile robots or any of these things. So I do think that system integrators will increasingly actually build robots themselves, like mobile robots, because they're getting easy enough and they are providing enough value in these smaller bespoke applications. So like a robot kind of like integrator, I don't think it really exists yet, but I do think it'll happen pretty quickly, especially as the software components get more and more functional and available.
So basically what I'm trying to say is 10 years ago, if I wanted to pick lettuce with a robot, I would open a startup company, go to venture capitalists and so on, shows there's a big market. But now what you're saying is it's a small side project, $100,000, $200,000, 4 months work. I build one, I sell it, they like it, I start manufacturing it in scale. It's no big deal. That's kind of what's changing.
Yes, but most importantly, 10 years ago, you would not be able to secure the capital and nobody would want to work with you.
Right.
Just because there's only so much lettuce. So now that you can do it with just a couple people and a little bit of time and a little bit of money, now people are interested because there is enough lettuce. Like the quantity of lettuce to the quantity of robots just was not anywhere near right before, and now it is.
Yeah, interesting.
All right. Okay, I think we're okay. So now I'll give a bunch of fun examples. This is a fun part. Okay, so we've talked a lot about the Roomba and the Kiva systems. Let me see if there's anything important here. I think the main thing is that before Kiva, there was a alternative. It was usually called a AGV, which stands for Automated Guided Vehicle. And that automated guided vehicle usually required the installation of an actual like kind of strip or tape on the floor. And that was similar to, like, I don't know if you've seen, they have these like invisible dog fences that you like draw a perimeter around your property. Same thing with the robot. Like you would actually have to put the wire into the floor to get the robot to stay over top of it. You could have done that, but it wouldn't be adaptable, and it would also be very, very expensive to do that in this large grid pattern. So Kiva was adaptive. Their way to navigate on the floor was very clever at the time. Instead of putting down wires or having like a laser to measure the distance from 2 points, they actually put little QR codes on the floor in a grid. So the robot has a camera. This is the other thing. They had a camera on the bottom of the robot, which is a big deal. So the camera would be pointed down at the floor and it would drive over the QR code. And then if it drove over the QR code and it was skewed a little bit to the right or the left, it would correct itself. And that was a really big piece of adaptivity and adaptive behavior that allowed it to get deployed at scale very cheaply and quickly and in an adaptive manner. So that's why the system was so killer. Is it was just so cheap to get out there, and it also was very high throughput in the goods to person application that it was built for. The Roomba, we already talked about that one. The thing about the Roomba is before the Roomba, there was no way to do it. Like you wouldn't build a giant industrial machine to roll around the house. It just wouldn't make sense. So the only way for the Roomba to make sense was to actually injection mold it out of plastic. And for anybody that's seen The Graduate, I have the screenshot from the movie down there. It's the one line to remember from that movie. The other thing about the Roomba is it takes an approach of doing numerous mediocre passes instead of like one really good one. And this is a common theme. So it's like, instead of it being a really good vacuum that has good suction and everything, like a door-to-door vacuum cleaner salesman would completely bomb if they had to sell a Roomba, because usually you like dump some dust on the floor and roll the vacuum over it and it has a perfectly clean line after. If you do that with a Roomba, there's still going to be some junk left afterwards. But the really important thing is the Roomba has enough time to just bump around a few times and make multiple passes. And that approach of many slow and mediocre passes actually winning the race enabled it to be successful. So that's a thing that like really wasn't there before, which is a new approach for a robot. Okay. I find this to be a very interesting robot, and one of the Newbot that is. And one of the things that makes it interesting is the whole thing can be additively manufactured. So you could just 3D print this whole robot. This is a robot that measures the temperature and humidity in a bulk granular material. So grain storage silos, if you want to actually know what's going on, instead of just measuring the temperature and humidity at one spot, usually kind of like at the outlet flue on the top of the silo. If you want to actually measure with much more precision through the whole bulk of the medium, you'd have to get tens or hundreds of temperature and humidity sensors and put them on strings and install them in this bulk granular media. This robot is a single sensor that actually rolls itself and kind of dives down into the granular media. And so instead of going from high infrastructure requirements, lots of wiring, lots of upfront cost, it allows you to go to a single tethered robot that can go anywhere in the media and get you the data that you need. This is also, again, a robot that you can build in your spare room. There isn't a whole lot to it. It's very simple, and it provides a lot of functionality. And the company that makes this, I think, to the having a proportionate amount of grain silos to the proportionate amount of robot people creating the first robot, this is now easy enough to do with a consumer 3D printer that this little startup exists, and it adds enough value in its application. This is the robot that I posted on Discord. This is a really important robot, and this is actually in the past week. This happened in the past week. So I don't know how many of you are familiar with Ocado. They are the largest online grocery. Maybe don't quote me on this. I believe they're the largest by volume, but I think they're the largest e-grocery fulfillment provider to date. They're based in the UK. They're now in the United States partnering with Kroger, and I think they're up to 3 CFCs in the United States, and then I think they have like another 5 or 7 in the UK. They have a pretty long and interesting history. They're also in a legal battle with AutoStore, a German competitor, which had a similar kind of entry. Oh, by the way, if it's not clear from the photo, the way this system works is they have a 2D grid, and then the robots roll X and Y. They can switch between rails on the 2D grid, and then they have a little gantry elevator that drops down and grabs bins. So they stack bins deep into wells. They can lift them up and move them over and dig them out. And that's how they actually store and retrieve groceries at very, very high density and throughput. They purchased a company called Haddington Dynamics 2 years ago. Haddington Dynamics made a almost completely additively manufactured robot arm, which I think it was not a very kind of functional or that good of a robot arm, but it did do the thing. It was pretty neat, and it was actually almost completely 3D printed, and they acquired this company. I have no idea. I have no involvement with them, so I have no idea, but I would think that their team talked with their fulfillment center robot team, and they've now yielded this robot, which is almost completely additively manufactured. So all of the spacey looking parts are generatively designed and shape optimized. They're printed on the HP multi-jet fusion process, which is a binder jet, it's a very cost-effective binder jet process. And the reason that they did this was, at least in their public materials, is that it makes the robot much, much lighter, and in turn makes the truss and rails that they have to build to create a fulfillment center much cheaper and lighter weight as well. So the entire system cost went down very, very heavily because they were able to make the robots lighter. And I would also argue, there's many other benefits if you can 3D print the whole robot. Like supply chain is a big one for a lot of people. So they can make spare parts very quickly and easily, and they don't have to worry about super long supply chains. They can just print a whole new robot and put it on the production floor. This robot is the most functional 3D printed robot I know of. Like they fulfill many millions of grocery orders, and this thing is going to be actually on the floor doing the job. So I think this is the first, and this is a really big deal of a 3D printed robot that's doing real things. You'll also note that they have a UR5 in their pick center. This is another thing they're doing that's kind of new. They're calling it on-grid pick, and evidently this it dramatically increases the system throughput, because instead of the little store and retrieve robots having to move bins over to the robot arms are collaboratively coordinated with these storage and retrieval robots, so that they can just come by and drop a bin next to the arm, and then the arm does the picking right there. So the mean travel distance goes down dramatically if they can just bring a tote adjacent to the arm and then move it back into the storage cell. So that's an example of really, really close robot collaboration, especially between two different types of robot that's going on. And that's something that you can only really see, you can only realize the value in that by running a simulation. So I'm sure they have a great simulation group that they went through that and made sure it was legit. This is a fun one. So this is the Pillbot. I think you've probably seen the pill cameras that you can swallow. The fun one about this is it actually has little thrusters. So this thing can swim around in your stomach, and you can kind of have like a little telemedicine submarine that you can swim around and move around. this is a great example of a robot that was built in the living room. There isn't a whole lot of components. It's very small, and it's also making use of the best, most modern lithium batteries that you can buy, and then very, very small and high performance motors. And that's I think this is a great example of a robot that's really easy to build and prototype now, especially using additive as well as using modern batteries.
Though this one, I wonder about making it at home though, because it's going into a highly acidic environment and it has to be extremely sealed, right? Otherwise, it could break down inside the body and you'd have like, I don't know, lithium contamination. I don't know if that's toxic or whatever. Is that an issue? Like, I wouldn't swallow this.
I'm not so sure I would either, but the team at this company, they did a webinar and they swallowed a robot live on the webinar. So that's pretty neat. I suppose it just comes down to how much do you trust your own work? This is a good little test of that.
How does it move? This one?
It has 4 little thruster motors. So they're an impeller with a closed shroud, but there's 4 of them, and they can kind of independently move. If you'd like, I could send some links to their YouTube channel. Below, they have a little demo running in their kitchen sink with some other the detritus for scale, and that they can kind of drive it around and show you how it's actually very good control authority, and you can locomote. Their vision is to eventually have actual surgical tools on the tip of this little robot, so you can actually swallow a surgical robot package to deal with, I don't know, a polyp or ulcer or something. I think the main use case now is to replace an endoscope to screen for stomach cancers and maybe colon cancers as well. The camera is currently not very good compared to an endoscope, but I know they're working to improve that.
I thank you. Is this their first iteration, or they have several iterations and maybe getting smaller and smaller over time?
Yes, yeah. I know they're still actively developing it. They're still pretty early. This is not like hasn't gone through clinical trials or anything. So they're still a pretty early company, but you can even see the difference between Rev 1 and Rev 2 that's marked here.
Okay.
There's some volumetric improvements there, and hopefully higher res camera as well. All right.
You know, it seems you know them, and do you know a bit what their challenges are? Because in the new boat trend you're exposing, it's also interesting to see how current companies are iterating and what their challenges are and what their what in the after the inflection point, what they can leverage to step forward, basically.
Yeah, I don't know them super well. I think I heard quite a bit about them, or even a podcast or something I listened to in the past year. But I do know they're very committed to it, and yeah, it's something that you can now prototype really easily. Like I don't know, it'd be a great question to ask them, like if they think they would have been able to get as far as they've gotten in this time frame even 5 years ago. To kind of gauge where that point is. To Meyer's point, this is not a robot in the strict sense. It is remote control. So this is actually a drone. It's just a submarine in your stomach. So it's like it's a remote control sub. But I do know they eventually want to incorporate some autonomous functionalities into it. I just thought it was an interesting example to list here, even if it's not a robot in the strict sense.
It's an interesting one. And we can see a challenge, maybe referred by Venkatesh earlier, about storage and the compute that you mentioned. But as these things are getting smaller, we still want them to be autonomous to some extent, and so we see some pressure on opposing forces here. Pretty interesting where it's going.
Yeah, actually, to Venkatesh's point, this is their issue is transmit bandwidth, which is due to the fact that you have to use a low frequency to transmit through the body, since we're saltwater bags and RF doesn't do very well with that. So they're sub gigahertz, they're like 900 megahertz or something, and the bandwidth is pretty bad. So they the transmit is the limitation there. The camera has a plethora of data. It's just getting it out in real time at a reasonable frame rate that's the problem.
Thank you.
Yeah. I think this is
Just
an example.
Just 1 second. The flip side is, of course, that if what you're doing is looking for cancer, the camera can identify non-standard pictures, weird behaviors, and send only them out. Okay, so
You're saying like on-device compute in this case?
yeah, doesn't have to be a lot of compute. Let me give you an example of a simple compute problem. When you're going through the large intestine, it's folded up like an accordion. So the question that they always have when they do colonoscopy is, how do you know that you actually saw everything? Well, this kind of robot, which has a combination of ability to move and just even a teeny bit of compute, could theoretically make sure that it imaged everything, that it saw everything.
Yes, and yes, I mean,
And if it's missing a
pursuant
bit,
to
it goes back, and if it sees, let's call it a flat polyp, what might be a flat polyp, it takes a picture from another angle. So
yeah, the issue here is the precision and recall, the false positive, false negative. So this is in this case, person to FDA regulations and whatever country you're in, their regulations. That's you would now be kind of guaranteeing a functionality with limited compute with a finite amount of battery. It would just, I'm just saying it'd be hard. I think that'd be a struggle for them.
mhm.
Because you would be making a claim. But we are getting kind of close in time. There are a couple more good examples I wanted to get by. So to talk about drones, I think this is an excellent application of drones. These are tethered, and this is a collection of robots that kind of slowly and gently and gracefully do their job. And having a lot of them is just fine because there's enough space and they're cheap. And if you have a modern kind of system approach, you can coordinate them so they don't bump into each other. So I think this is an excellent example of tethered drones doing an actual functional purpose. And the kind of the wrong approach is embodied by a company called Abundant Robotics. I don't know if I've talked about them before, but their approach was actually to use a single end effector and move it as fast as possible. And that just simply did not work out by any sense of the word. I could send some videos about what their system looked like later if you would like to see that. But having 60 drones that are kind of gingerly picking fruit off of the tree and not damaging the fruit, that's actually a big concern in this application. You have to be very gentle with the product. That is much preferred and actually very cost effective compared to building a giant, expensive carbon fiber gantry that can move quickly and grab things and it's dangerous. This is also a robot that you could build in your garage. This is very cheap, cost effective, easy to prototype. And it's putting the emphasis on slow and cheap versus, many and slow versus few and fast is what makes this approach come to light. Okay, this one I listed because I think it's actually kind of a bad approach, but the approach it embodies the Newbot spirit, if that makes sense. Does anybody see why this would never work? Like why this company is going to have serious problems?
There is a need for infrastructure. I mean, it's not only the robot, it must have a rail all over the place to be able to work, right?
But that's just it. So this is a retrofit system, which is one of kind of like the, Newbots, I would say, in spirit, minimizing infrastructure. So using existing infrastructure and dealing with it is a good attitude to have. However, if you notice, and this is something that they could solve, but if you notice their current robot that you see here, it has a fixed pitch between shelves. And if you go in any fulfillment center, the shelves usually do not have a fixed pitch. So some shelves are very far apart, some are short together, and therefore you end up pinning yourself in retrofit hell by trying to, convince the customer that they have to make all their shelves the same pitch, and you'd be better off just ripping the whole thing out. So if they were to change the robot to be even more adaptive, then it might work. Or, in this application, dare I say, you could even use a tethered drone, since you could actually send a lot of power up a cable. You could lift some serious weight, big airflow, but you could lift some serious weight. Or you could just automate. You could make a forklift become a robot. That's a pretty common. There are like 5 companies working on that. But yeah, it's like it's a cool idea, and it does make sense. Like it's a climbing robot that climbs on the existing shelving, but then you actually look at it, and I think the approach ends up inhibiting its success. Okay. This is my main example of like in an industry that traditionally uses a giant machine. That for a wide variety of reasons, you actually would benefit from using numerous smaller machines. So this is a company called Pliant Energy Systems. They make this cuttlefish robot. It has, instead of like a propeller or spinning blade, it actually undulates a elastomeric plastic strip, and that's how it moves around. And then one of the applications that they're looking at going vertical on is the harvesting of polymetallic nodules on the ocean floor. Traditionally, they have this giant, like, it looks like, so this is a person, by the way. These 2 red things are people. That's how big that thing is. They drop that, effectively, it's like an excavator down on the ocean floor, and it has these giant suction tubes that like suck up these rocks off the floor, and then they send them up a tube to the boat. The issue is it creates a giant dust soot plume that destroys the environment, and then everybody gets mad. So instead, they want to have this swarm of delicate little robots that just undulate around and pick the little polymetallic nodule potatoes off the ocean floor in a very non-invasive way, in a swarm-like and adaptive manner. And that's what they're working towards, and getting away from this very large machine. Again, this is an example of you're going from a machine that would require several millions of dollars and space to build, down to you build one robot in your garage, and then you can make 100 of them and have a comparable system throughput. So this is a pretty interesting robot, just in a lot of ways. I think the other benefit to having a swarm in this application, you'll encounter this in I've met some like deep sea, subsea ROV people lately, and if you talk to anybody that does subsea work, the first thing is reliability, because the cost just per every second that you're deployed is immense. So if anything fails when it's on the ocean floor, it's disgusting how much money is spent every second being deployed on the ocean. So they are so risk averse. All of their hardware is from 30 years ago. They worry about, the potting material on their semiconductors having voids, because when you're down at 8,000 meters, any pocket of air can explode and then the whole machine goes down for a few hours. So like they are so risk averse, and having a robotic system that if one or two robots died, it wouldn't kill the mission. It would only take the system throughput down by some percentage. So that's actually a pretty big deal, is the fault tolerance associated with mini robots. And that's it. So, let's see. I listed this one. So this is Roomba++. I don't know if anybody's seen this company. They're pretty cool. I think this will probably be the most successful home robot to enter into the space in the next few years here. Amazon's little home robot, nobody will care about it. It's silly and overpriced. It's very sad there in the bottom. But the Labrador robot makes a lot of sense. It's very kind of low tech, easy to prototype parts. Again, it's a small robot. It has cameras. It's adaptive. It can navigate around the house. And then it's kind of like a Roomba, but with an adaptive autonomy stack that can move around your house, and then just move a little plate of dishes onto itself and onto it, like off to a shelf. It has like adds a little bit more functionality that's very meaningful, and so it can actually be useful to people. But we'll see how they do. They're a bunch of XI robot people, but that's kind of a side example. All right, that concludes my Newbots discussion.
That was very, very
Anybody?
interesting. It's a very interesting look at what's happening out there. That's all I have to say.
Are there any questions or thoughts?
Do you see any recurring issue with new boats? I mean, perhaps more precisely, it seems that there are more and more new actors, okay, because now we can do them in our garage, basically. So it should multiply the number of actors on the market. And do you see what kind of challenges they are facing over and over? It's like before ROS, basically, it was much harder to get started with the software stack for a robot. With ROS, we at least we have something to look at and a community behind it. But now with these new boats, we can make them cheaper in the garage and so on. But we talk about swarms. Swarms is, I think, brings a new set of challenges compared to traditional robots, things like that. So I was wondering whether you had some insight about the kind of problem that come over and over today with the new boat makers, let's say.
Yeah, I think in one or two sessions ago, I mentioned that the contemporary issue that I see people encountering today, like over and over again, is kind of like the robot version of DevOps, or like robot ops. So actually managing multiple robots in the field. And that includes all of the laundry list of things, like deploying containerized images of software, monitoring, synchronization, traffic mission planning, traffic control, air traffic control, all of that group of tasks that emerges once you have a product that's actually comprised of multiple individual robots in a system. That is the current thing that I see people hitting the wall against a lot. And there are a number of companies that are trying to meet that need. There's a lot. So there's like In Orbit, there's
AWS, in a way, with RoboMaker is touching on that. And recently there was a funding of a company in Israel. Maybe Fabian remember the names, but they have a product called Nimbus that covers a lot of that. And apparently they got a big round recently, perhaps because of the trend you've just shown here. What was the name?
Yeah, it's something where everybody's rolling their own, and I think as people increasingly realize, like, yeah, the apple picking drone swarm, I don't know of anything that I could point at that would just solve that problem for them. That would just be like, yeah, you can, pull in this package. And this is also, I remember this specifically, we were talking about this, I think Mayor, we were talking about this. There's no like decentralized master controller. That's just a virtual image that gets taken care of for you. You have to deal with setting up a server somewhere or designating a robot to be a master. So there's no like masterless like swarm controller implementation that I'm aware of. And then you're paying some company to help you deal with, you have to have a server that's on premise, or in the Apple example, you'd have it bolted to the tractor or something that has the tethers, and that would actually handle the air traffic control task. The other one I'm thinking of is Formant.
Oh, yes.
Formant.
Yes. Thank you. Another question, what about self-driving cars? Because they appear on your roadmap, but after in the new boat section, do you see any maker being in the new boat mindset?
Yeah, I kind of avoided the whole topic of AVs. AVs are really interesting. So AVs are driving a lot of the Newbot, especially the enabling technologies. Let me stop this screen. There we go. You're asking about like the premise that you should be able to build a robot at home, and how does an AV come into play, or like, can you elaborate?
In a sense, but maybe at another scale, because if we look at Tesla, for example, Tesla was not born a car maker, okay? And so sorry, I'm a bit stretching the idea here that the car industry is very old, okay? It's more than 100 years, okay? And Tesla is just a newcomer, basically, in terms of years. It's not 20 years old yet, right? And basically, they were starting making planes, if I remember well. But after they moved to the car, it was very minor. It was like in their garage, okay. And I think back then they were on electric cars, not yet on self-driving. But by the time they were pushing on self-driving trials, they were still extremely minor on the as a car maker, okay. And still now, I think it seems they have a pretty unique approach on robotics, okay, pushed by their CEO, but also so many companies and all the incumbents in the industry are following them, basically, right? So in that sense, there is this distinction between the garage in terms of the cost in the car industry, in a way. Maybe I'm stretching too much, sorry.
Yeah, I think with my meme here, the point really is that Tesla is a robotics company and always has been. I'm very happy that I think a couple people were saying they're glad that the hype machine has now literally called that out with the Tesla bot, the humanoid project they're working on. So, that's like literally a robot in the sense that everybody can understand. Like, yeah, Tesla builds robots and their cars are actually robots. I mean, if you listen to Karpathy talk about the stack that they're building, they're like, yeah, they're effectively building like a yak. It has very basic like intelligence that you would have. It's like a 1 horsepower car. It like has 1 horse brain worth of intelligence to it, is what we're almost approaching. But yeah, like the thing is, once these become a level 4 or 5 piece of equipment, just by the sheer shipping volume from Tesla, they will be one of the largest robot manufacturers out there.
Yes.
If it really is like a level 4 or 5 car. I think the annual shipment of industrial robot arms is still sub million. It's like between 500,000 to 1 million annually, excluding collaborative robot arms. But let's say it's under 1 million. Tesla alone is shipping, they're up there at like what, 500,000 units annually now, and it's just getting larger. So in terms of just like the raw numbers, they will become the largest robot manufacturer out there. And then the humanoid robot, that'll be pretty interesting. We'll see what happens. But I'm really glad that the attention is getting put on robots now, because that's where it should be. And it's really disambiguating that that's what Tesla is. They're a robotics company.
So this is like the opposite of Newbots, unless the Newbot is using the Tesla bot as a component.
So the Tesla car is, I mean, it is a Newbot according to many of the laws. It does have some conflict. So the big one is that it's using cameras, lithium batteries, and modern magnetics. Those are like the 3 big pieces of technology. And then I think we'll see what happens when it comes to operating as like an AV fleet. But they have the connectivity and the capability to do that. So the whole scheduling and central optimization thing is, just a few clicks away for them. But it's like, is the Tesla car a Newbot? I think so. I would, even though it does definitely violate it definitely violates the built in a garage.
Yeah.
The thing about that is, if you kind of separate the brain of the car from the car itself, it gets really cheap. So like the actual brain and cameras and all that's on the car are actually pretty cheap, just like on raw BOM value. Worth mentioning, John Deere announced the first fully autonomous tractor at CES. It was kind of interesting. They've only been at CES for the past like 4 or 5 years, I think. So John Deere announced their autonomous tractor, and guess what it's running on? It's running on a little, compute module about the size of a backpack. That's it's just an NVIDIA Jetson sitting on the front of the tractor, integrated into their CAN bus and some extra cameras. So the actual compute, the brain and the perception on Tesla Model 3 and the John Deere tractor, it's only, probably, well, on the Tesla, it's sub $1,000, right? On the John Deere, it's probably $1,000 to $2,000, but it's actually very cheap and garage level, if you will. And the hardware that you would see on a sidewalk delivery robot versus on a Tesla car is very, very, very similar. So that's what I mean is like the brains are actually very, very similar, even if the skeleton and the muscles are pretty different. So
Commodity.
yeah. Well, okay. The Tesla rolls their own, right? That's not commodity. Tesla does not use NVIDIA hardware. John Deere does. So John Deere is using the commodity hardware. Any other questions or thoughts?
Yeah, I was posting a lot of my comments in the chat, so we'll save the transcript to Rome. But one point I wanted to flag is a slightly different way of looking at Tesla is to compare it to Comma.ai, and I've been very impressed by what they're doing. And Comma is kind of like OEM AI for driverless cars, and their sort of AI strategy is very different. And I think based on your definition, yes, driverless cars do fit the physical definition of your Newbots, so the magnetics and lithium batteries and things like that. But in terms of like the, I don't know, logical architecture, I think they don't, because they kind of like exploit the smartness of the driving environment, because there's roads and signs and lane markings and shit like that. They're able to exploit all that to make the AI part somewhat separable from sort of the mechanical part. And that makes it, in some sense, sort of an unfairly easier problem than the other robots you've been describing in your examples, which kind of operate in a much more, messy, unstructured environment with fewer rules, which means that when you do design, you kind of have to like accommodate like the complexity of the particular environment in both the hardware and software, and they end up co-evolving in a certain way. So even though the hardware might be commodity, you do kind of have to like put them together, in a more bespoke way than EVs. But this is a longer discussion, and I think the jury's still out. And one of the ways I think this will get sorted out is, will the Tesla model of doing autopilots win out, or will the Comma model of doing autopilots win out? And right now, I actually don't know. Like the latest I've seen from both, I can kind of think of arguments why either might be good or not. But right now, I like the Comma approach better somehow, which suggests to me that it's, at least on the software side, it's not as much of a new bot, or driverless cars are not as much of a new bot thing as some of your other examples.
And Comma is, in the strictest sense, the most literally out of a garage company I can think of in the AV space, if you could even say it, they're in the AV space. So
yeah,
if you listen
remember,
to
they're working on the
George
generic
Haas
AI,
rant
right?
about,
They're working on a generic AI that can be retrofitted on any car. They're not co-evolving a physical car with the autopilot to run it. So that's why your other examples, I see kind of like a strong coupling between the hardware and software. You kind of have to do both together, even though one is the commodity piece. But yeah, maybe that'll change. So that's, I think, a good topic for future discussion. And the way I would frame the discussion topic is the software/AI layer kind of a general purpose OEM kind of thing that can basically go onto any hardware chassis? So something like ROS+++, like, you just take it, you give it like some details of the hardware, it adapts, and then you can program it very easily at a high level? Or is it the case that you have to co-evolve the AI with the hardware as you're designing it? And I don't know, philosophically, I like the latter path. It looks more vertically integrated, but for more complex applications, I suspect it'll be a little bit like that. And partly because if you look at biological brains, yes, there's some generality to mammalian brains, but in general, animals do seem to have brains that are sort of co-evolved with their bodies. So that to me is a strong precedent for how robot intelligence might evolve. But I don't know, this is like all speculation for what might be the case 10 years from now.
there has been quite a bit of work on kind of like hardware self-discovery, I would say. I mean, a large function of ROS, I think we've all feel like the majority sentiment in this group is that it's actually more of a framework and an operating system, but ROS is really about plumbing things together. And, like the ROS+++ example is that, yes, it actually does self-discovery. And so there are some examples, at least in academia, where you have robots that you can arbitrarily connect the hardware and linkages together. it then performs some perturbance moves on its legs or arms and can eventually figure out the kinematic chain and where things are hooked up. So it is actually a software package which can just learn its hardware configuration automatically, and then actually kind of self-optimize. This is also called online calibration in a lot of things, where you actually, even in like a Tesla car, this is a really big feature, is online calibration, where you actually build the product and then don't do any calibration in the factory. You know it's within some margin, but then when you actually use the product in the field, it looks at the errors between the cameras and things and figures them out on its own. And that's something that is pretty commonly used in a lot of cases today, especially because, like, you know, if your car gets hit by hail or something and it moves the camera a little bit, it needs to still work. But if you have good software, it can just see the kind of like global, you know, DC bias in the image shift and then adapt. So.
And I think this is the path that Meyer and Eric are pursuing. Like Eric's sort of like constructing a sense of the body from like sensor inputs without like preconceived notions of what they mean by, like, you know, statistical analysis. So yes, I think that's definitely a path that's going to be pursued, and it's going to lead to very good robots along one branch of evolution. But just going by like the solution biology has found, I suspect another major path of the evolution will be problems and cases where that kind of like online learning approach simply won't be good enough to like actually learn the particular physical body, and you'll need a bit of coevolution. And the kind of example I'm thinking would be closer to something like, can you actually transplant like a human brain into sort of an elephant body and expect it to actually like adapt and learn? And I think while brains are plastic, and humans who have like, you know, who lose an arm or a leg or like lose a sense, they kind of rewire very radically and can like really adapt to very different morphologies of their physical body. I think there's limits to that, and it's not clear to me where those limits are. And that's, by the way, actually a good segue to what I wanted to discuss next week in my session, which is, you know, the science fiction 3 laws kind of stuff. Because Asimov has one conception of like brains that are fairly closely adapted to bodies. And if you look at other science fiction series like The Culture, in The Culture, the brains are pretty much abstractable, and they go from like one ship to the other, or go from a ship to like a space station or something like that. So I'll cue that up as a teaser for my topic next week. I think it's an interesting comparison.
And by the way, to just bounce on that, this is where deep learning may come into play. And so maybe also the interest into the Jetson Nano, in the sense that if we have a generic software component that can adapt to several hardware, after how well it can adapt, this is where the deep learning glue can do the fine tuning. Okay, not immediately, it takes some co-evolution, but the co-evolution doesn't need to be in the design phase. It can be at just around the deployment phase, in the sense we have a hardware which is hard, expensive to make. Okay, even in the garage at first, in terms of time, the hardware takes a lot of time. Okay, and we could have the software components that, with some online calibration mechanism, perhaps facilitated with something like deep learning, could do the fine tuning in the end. So I'm trying to say that it's a different look, but perhaps not incompatible. Different looks, sorry, at the same point, but not incompatible. Joshua, would you have some resources about the online calibration? I've just had a quick look, but it seems a wild topic because calibration is across many domains, right?
Yeah, I could see if I could pull something up.
I'll ask on Discord later. Thank you.
Thanks.
We are 1 hour 45 minutes in this great meeting. Do we have some other questions? Challenging questions, if possible. It's getting
This
late.
was great, all, but I'm going to drop off.
Yeah, so perhaps we can wrap up for today.
Yep.
Very good. Thanks, everybody. I hope it was interesting.
Yep.
It was
Thank
great.
you.
Thank you.
It was great. Thank you very much.
you guys next week.
Thanks.